The last part of problem 9, and we'll okay. We've got a new set of XY axes because I've told you that now the x-axis is supposed to be horizontal, the y-axis vertical. In analyzing the motion on the incline, that's not what you want. You want the x-axis parallel to the incline. It's in the direction of motion because that gives you y equilibrium. So you want equilibrium in one direction or another if you can possibly have it. However, we're trying to make a point here. Now, your delta S is still going to be 1.6 centimeters down a 5% incline. And your weight vector is going to be negative 0.5 newtons times, having a bad time with I and J today, times the J vector. Okay, so W is down like this, and delta S is like this. Now, your dot product, it's probably worth noting this. Is independent of the coordinate system. It's kind of an important idea. The independence of a coordinate system comes up in a lot of physics, okay, especially in things like general relativity and so forth. And of course, we're not doing that. And you know, as engineers, you're not likely to use general relativity or even take a course that involves it, unless you're just really interested in it. Okay, so, but there are things that we will encounter where the independence of coordinate system is important, and this one is actually one of them. Okay, so back on track here, we have this vector and we have this vector, but we haven't put the delta S vector into I and J components with this new set of axes. Okay, well, pretty easy to do that. A 5% incline is a small incline, and in that case, the opposite side of your triangle, or the in this case, well, this component of your delta S, which would be the J component in this case, is very close to 0.05 times your magnitude of the vector. And yeah, that goes along with what I told you at the beginning of the problem. It was in the problem. So we're using that approximation. If you want, you can take the arctangent of 0.05 and then take the sine of that angle, multiply it by 1.6 meters, and this is what you're going to get. You get maybe a 7, some 9s, but it's going to be very close to the 0.08. Okay. So we just bypass that difficulty. We use this small angle approximation, which is something that's used a whole lot in physics, okay? And hopefully know enough trigonometry to know how that reconciles. The I component is just about negative 1.6 meters. That's pretty obvious. Going at a 5% incline, it's even shallower than what I've got here. It's a very shallow angle. The magnitude of the vector and the magnitude of its x component are going to be practically identical. The x component will be just a little less than the magnitude, but it's just going to be a fraction of a percent less. Okay, and you can verify that also. You can work this out by the Pythagorean Theorem. If this is your y component or j component, and this is the magnitude of the vector, then the square root of this square minus this square is going to equal the x component, magnitude of the x component. So go ahead and work out the square root of 1.6 squared minus 0.08 squared and see how close that is to 1.6, at least to make it convincing that the small angle approximation works here. Okay. Having gotten that, well, the rest of the problem is fairly simple. So now we know that delta S is going to have to be negative 1.6 meters times I minus 0.08 meters times J. And your weight vector is what? It's negative 1.6 meters times j. So now, what's the weight component? Dot, and not the weight component. This is the actual weight. We're not taking just the component of the weight parallel to the incline now. We're taking the whole weight, and we're going to form this dot product. So what we get when we do the dot product of the weight with our delta S vector, we're going to take negative 1.6 meters times j, and we're going to multiply that by negative 1.6 meters times I minus 0.08 meters times j, and we're going to get 0.08 meters times 1.6 meters, and it's not meters. What's going on? This is newtons. Yeah, doing the unit calculation, I was getting meters squared here, and at that point I knew enough to know that I'd screwed something up, which I'm doing a fair amount of, but some of this is okay for you to see because you need to be able to do the same thing. You need to know when you've screwed up as quickly as possible. Okay? And following the units is one way to do that, as I've just illustrated. I didn't make the mistake intentionally like I facetiously claimed to do. It was an honest mistake, but okay. Now I was thinking ahead to the calculation. 16 times 8 is 128. So that's going to be I'm getting 0.128 Newton meters, which is 0.128 joules. And again, that doesn't even begin to match what I got previously, so I'm going to stop for a minute and figure out where I've completely screwed this up. Okay, there's obviously had to be some big mistake, and hopefully you saw it when I first wrote it down. The weight is not negative 1.6 newtons. I was writing the 1.6 meters, then I corrected it to newtons without thinking that the 1.6 is in meters, and that's not a force. The force is the weight, which is negative 0.5 newtons, and then that correction follows very simply. It goes here, and when we multiply 0.5 by 0.08, we get 0.04, so we get 0.04 joules. And yeah, I'm not sure that the camera is quite pointed that low, but there's the correct result, and of course that does reconcile with the result we obtained previously. Now we have the same delta S vector, and we could multiply that by the net force vector or the frictional force vector in either case. But of course the net force vector would be in this direction. The frictional force vector would be, well, not necessarily in this direction, but along the line of the incline, which is going to be along the line of the delta S displacement vector. So you should see how to do that. I'd suggest that as just a quick little exercise. Figure out what the components of the net force vector for this situation would be, and figure out the components of the frictional force vector. And notice that in this coordinate system, the net force vector should equal the weight vector, the whole weight vector, not just the component, plus the frictional force vector, plus the normal force. Those are the forces acting on the object, and those forces can be analyzed in this horizontal vertical coordinate system.